Now we have finished just now we have finished structural isomerism. Uh, Now we'll come to that is your stereoisomerism. You have seen it in that is Werner's theory also, that coordination compounds can be arranged in a three-dimensional space. Got it? They are directional in nature. You have seen it in coordination compounds. They are directional in nature. So hence this shows what you can say stereoisomerism. Got it? They can be arranged in a three-dimensional space. They occupy different spatial means spatial, that is three-dimensional space. They occupy different spatial, what you can say, position around the central metal ion. Got it? Which occupies the ligands, that occupies different positions, spatial positions around the central metal ion. Whatever it is, in short I can say they are three-dimensional in nature. Got it? And they can be arranged in a three-dimensional space, that is the coordination compounds, and hence they are said to show stereoisomerism, so to say. Now stereoisomerism is two types, already I have said, that is geometrical isomerism and that is your optical isomerism. The first one we are going to come to geometrical isomerism. So geometrical isomerism again is two types, you know that, cis and trans. Now we will see geometrical isomerism in two types of complexes. Alright, as it was said in the Werner's theory, we have seen it, that we have got 4 coordination spheres and 6 coordination sphere. Listen carefully. 4 coordination sphere means when the central atom is attached to 4 ligands. Alright, it may be same or different ligands, that will depend. But first I am explaining you what do you mean by the word 4 coordination spheres, which said to be. Means that the central atom is attached to 4, what you can say, ligands in a 3-dimensional space. That is called as 4 coordination spheres. Let us say the central atom is your M, metal atom is M, and different atoms or the group of atoms which is attached to the central metal atom by the help of the coordinate bond, we can say that is nothing but A, B, C, D, small a, small b, small c, small d. They are the ligands, we can say that. Got it? 4 ligands, we can say. So in this way, when the central metal atom is attached to 4 ligands in a 3-dimensional space, and they form different arrangement, they have got different spatial arrangement. Again I repeat the word spatial when I say spatial here. Alright. So in this way they show different arrangement in a 3-dimensional space. Means as I said you already, that is they are directional in nature. So hence it is called as 4 coordination sphere. 4 different ligands attached to the central metal atom. Now similarly, if suppose 6 different ligands are attached to it, then it is called as what? 6 coordination spheres, we can say that. If 6 different ligands are attached to the central metal atom, got it, and they are directional in nature, they show different compounds, then they are said to be 6 coordination spheres. I think it's clear what is 4 coordination spheres. The first one will come to the 4 coordination spheres. Now under 4 coordination spheres, whenever we say 4, that means in our mind straight away it comes AB4 molecule, which we studied in class 11. AB4 molecule, where the central metal atom is A and the surrounding atom is your B. So AB4 molecule, and AB4 molecule is tetrahedral in nature basically. So the first thing comes in our mind is whenever we say there is 4 what you can say coordination spheres, this example comes first in our mind, that is AB4 molecules, and it should be tetrahedral in nature. But let me say you here, tetrahedral complexes does not show geometrical isomerism. Tetrahedral complexes does not show geometrical isomerism. Square planar complexes shows geometrical isomerism. Tetrahedral complexes does not show. Why? You may write it down. Tetrahedral complexes do not show geometrical isomerism because all the 4 ligands lie at the same distance from the central metal atom. All the 4 ligands lie at the same distance from the central metal atom. Therefore, no case is observed where a tetrahedral complex is found to show this type of isomerism. Means the 4 ligands will be at equidistance from the central metal atom. So what will happen? You might be thinking, what will happen? We cannot differentiate into cis and trans. Alright, we cannot differentiate into cis and trans. Alright, that's the thing. It should be resolved into cis and trans. Alright, so here then only we will be having isomers now. Alright, so hence tetrahedral complex does not show geometrical isomerism because all the 4 ligands are at equidistance, at same distance from the central metal atom. Got it? So hence geometrical isomerism is very common in square planar complex. Got it? So, however, in square planar complex cannot exhibit geometrical isomerism. Got it? So, what you can say, why? Because there are certain molecules, even if they are square planar, but they do not, what you can say, exhibit geometrical isomerism. Again, one change. Got it? First of all, I said tetrahedral complex does not so. Then I said square planar complex shows geometrical isomerism. Now I am saying in certain square planar complexes also does not show geometrical isomerism. Why? Because again the same answer. They cannot be resolved into cis and trans. So which are those particular complexes? Got it? Which do not show geometrical isomerism. For example, it is MA4, where A is a ligand, M is the central metal atom. Mind it. MA3B, again B is a ligand. Got it? And MAB3. It cannot be differentiated into cis and trans. You may write it down and see that it cannot be differentiated into cis and trans, where A and B, already I said you, they are the monodentate ligands. That also I am making it very clear. And it is not only a ligand, it is a monodentate, a unidentate ligand, so to say. So what you find is that that is square planar complexes of the type are unable to exhibit geometrical isomerism, because here we cannot, what you can say, differentiate in cis and trans. That means they do not exist in cis and trans form. We can say that. Clear? They exist in only one particular form. Now, so tetrahedral complex does not so. Square planar complex shows. But square planar complex, this also does not so. Then, which particular complexes shows geometrical isomerism under tetrahedral, under square planar complex? Now I am coming to the point. Alright, first I said you the answers of the reasoning questions. The question may be reasoning in nature, that this why it does not so, why tetrahedral complex does not so. I give you the answer for the reasoning question in the first part. Now I am coming to, that is, which complexes shows geometrical isomerism. Now see here. Complexes of the type. Here I am interested in the complex, not with the simple ion. Understood? Clear? So Ma2B2 N plus minus. Anything, it can be positive or negative charge. And A and B are the monodentate ligands that I have said you already. Alright? M is the central metal atom. Alright? So here basically in 4 coordination sphere, the central metal atom can be Pt, can be your iron. They generally come under 4 coordination sphere, so to say. So Ma2B2 N plus minus. So let us take here Pt here, and A I am taking it as NH3. Got it? And B I am taking it as Cl. So what it should be here, what you find is that Pt NH3. Now NH3 is a neutral ligand, you know that. That is, NH3 is a neutral ligand. Got it? So as NH3, it forms a neutral ligand. Got it? Pt is a 4 coordinations, that is the sphere, so to say. So its oxidation number is 2. Here Cl oxidation number is -1, -1 is -2. So -2 and here +2. 0, neutral. Got it? So now this is what form? This is nothing but we can say it is the cis form. Got it? We can say it's a cis form. This particular one is the cis form. This one. This one is a cis. We can say. You can write it in this way also. NH3 you can bring it here and Cl you can bring it here. So these two Cl will be one side and NH3 will be one particular side. That also can be done. Okay? Understood what I said? That is, NH3 you can bring it here. So 2 NH3 will be one side and 2 Cl will be one side. That is also a cis. We can say that. Now in case of trans, in this case, what you can do is that Pt, here it is NH3, here it will be Cl, here it will be Cl, and here it will be NH3. So what I have done it is that I have interchanged it. In trans, I have interchanged it. This two I have interchanged. Alright, so in this way, you have read it in lower classes, what is cis and what is trans, you know that. Alright, if you want, you can just draw a dotted line here. Alright, which shows that it is a square. So it is a square planar complex, as you can see it here. Alright, so this is a cis and that is a trans isomer, so to say. Now, next is, we will be seeing Ma2BC. Now, one B I will replace with another ligand. That is C, we can say that, N plus minus. Alright, so 1B, I will be replacing it here. So what will I do is that, here Cl, Pt, let me write a little bit below. So Pt, here it is NH3, here it is Cl, here it is NH3, and here it is 1. I said you that 1B, the B I am taking it as Cl, so I am replacing it. Again, same thing is neutral, same thing. Cl is -1, Br is -1, Pt is +2, 0. So you find that is neutral in nature. Now, how it is cis? Because it is not necessary that both the sides it will be same. Here one side is same, you can see it here. One side is same. So it is a cis isomer, we can say. You can draw a dotted line here. Alright, trans, now I think it is clear to you what I want to do. In case of trans, it will be NH3 here, then here Br, and here it is Cl, and here it is NH3. See, this is your trans, this is your cis. One of the diagonal is same, we can say that. One of the diagonal is same. Got it? So Ma2BC, we can say that. Clear? N plus minus. Now, next, the two types we got it. Now, what will be the third one? You can guess it. It will be MABCD. One in the previous case, one B I have replaced with one C, a different type of ligand. Now, I'll be putting it here MABCD, N plus minus. MABCD. Again, ABCD are monodentate ligands. Now, same thing. Let me take it here PT only. I'll continue with PT itself. So, let us say this is NH3. Let us say this is Cl. This is your nothing but Br, and let us say this is your I. Okay. So, now next is this is cis. I'll tell you how it is cis. Alright, you might be thinking how it became cis. So, it is NH3. Here it is Cl. Here it is Br. Now I'll replace it. This one I'll make it as I, and this one I'll make it as Cl. Now this is your trans. Now look at the board. So here what you find is that all the three are halogens. All the three. So these two halogens are on the same side. I said one side if it is same, it is okay. Then it's cis. Alright, so these two are on the same side. These two halogens, not the same atoms. They belong to the same group. Halogens are on the same side. It is cis. Now same these two halogens are diagonally attached. It is called as what? Trans. We can say that. You cannot take this two. It is different. You have to take this two. So this two is cis, and this one is your trans. We can say that. So it is coming under MABCD. Got it? Now next. After that we'll come to the next one is your MAB whole twice. N plus minus. Now AB is what? Now till now we were doing monodentate ligands. AB here it is a bidentate ligand. So hence I have differentiated. Monodentate I am keeping it as a small letter, the small alphabet, and bidentate I am keeping it as a bigger alphabet. We can say that. So in this way the capital letters. So here what will I do is that is bidentate ligands, let us say, which will show geometrical isomerism. That also you need to keep it in your mind. Got it? Bidentate ligands. So here what will I do? See here. That is I'll start with NH2, CH2, then CO, and this is O. Now again it is NH2, CH2, CO, and it is O here. So NH2, NH2, OO are on the same side. NH2, NH2. So what is this? It is nothing but known as NH2, CH2, COO. What is that? That is nothing but is your glycine. We can say that. We can write it in short, in abbreviated form, PTGLY whole twice. What I can say? PT within bracket GLY, because the abbreviated form of glycine is GLY. PTGLY whole twice. Got it? Fine. Now this is your cis. This is said to be S. Now here this is same thing, PT, and here I will take NH2, CH2, CO, and here I am putting it as O. Clear? Now I will start from O here. O, then CO, then CH2, and here it is NH2. So see here, NH2, NH2 diagonally, OO diagonally. Alright, so it is known as what? Trans, in this way. Alright, it is coming under trans. So this is about your 4 coordination spheres, so to say. 4 coordination sphere under that is geometrical isomerism. Now, next is we will see 6 coordination sphere. 6 coordination sphere. So 6 ligands will be attached. Here also, so to say, That is, it will be an octahedral complex, definitely, because generally when I say 4, the word tetra comes. I said you already. When I say 6, then the word octa comes in the mind. So when 6 ligands will be attached, it will be an octahedral complex. But here also MA6, MA5B and MAB5 does not show what you can say geometrical isomerism, because they do not have different spatial arrangement in space. We cannot arrange the ligands in different spatial element. In short, I should say they cannot be differentiated into cis and trans. What I said, MA6, MA5B and MAB5 does not show geometrical isomerism, because they cannot be differentiated into different spatial arrangement in space. That means they cannot be differentiated into cis and trans form, we can say that. So hence they do not show this or this octahedral complex. Even if they are octahedral complex, got it, attached to 6 ligands, but they do not show geometrical isomerism. Then which one it shows? It comes, that is your MA4B2 N plus minus, where A and B, again that is same thing, they are the that is monodentate ligands, we can say that. Now here generally for there is 6 coordination spheres. As I said, for 4 coordination spheres, the central metal atom we take it as iron, platinum in this way. Here we will be taking it as cobalt and chromium, we can say. Got it? We need to see that they should be stable in nature. Understood? That is what you need to see here. Clear? So here I will be taking cobalt, and first let me draw for the 6th one. Got it? This is for the 6. I have done it. See here, the 6 ligands, the shape I have done it. You need to draw the shape first. Understood? That is very important, because it should look like that it is 6 coordination sphere. Like here I have taken Cl, 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 Cl. This is your A, and B I am taking it as ammonia. B I am taking it as ammonia. We can say that. Now, what you find is that it is a cis isomer. This one is cis isomer. This particular one. Now, what should be the code? There is a number. There is a charge. Now, what you find is that here cobalt is that is Cl is minus 4. 4Cl minus 4, and ammonia is 0. Got it? So, and here cobalt will be what charge? Same thing, plus 3. So plus 3 minus 4, it will be what? Nothing but minus 1. Understood? This is plus 3 and this is minus 4. 4Cl minus 4. So minus 4 plus 3, it will be how much? Minus 1, because ammonia is neutral. We can say that. So in this way, it is your cis isomer. We can say that. Clear? Now, next is we have taken it here. That is your this is your trans isomer. Sorry, I am very sorry. This is trans isomer, because diagonally it is same. Diagonally it is same. This is your trans isomer. The first one I have done it as trans. Now I will go for, what is that? That is nothing but your cis. Very simple. What will I do? That in case of that is cis, what I am going to do is that I am going to bring this to Cl here, this to Cl here, and ammonia here. Finished. Done. Understood? Just you have to apply a little bit of common sense. So what I said I'll do here, first let me draw the dotted line. That is, here it will be Cl, here Cl, here also same thing Cl, here also Cl, here NH3 and NH3. Same thing plus charge. This is your cis, we can say that. So what you find is that the diagonal is not the same. Here diagonal is the same. The diagonal is the same means it is trans. Here the diagonal is not same. So hence it is coming under cis, we can say that. So this is coming under MA4, that is B2. Similarly, we can also have MA3B3. Alright, we can also have MAA2A2, we can say that. Clear? So still some more examples we will see it. That is MA3B3. I have to be fast. MA3B3, we can say that. That is MA3B3. The same example I could have taken here. The same example, that is cobalt. Just I rubbed it for your easy, what you can say. I have taken, this is Cl, so Cl, Cl, Cl. This is NH3, NH3 and NH3. Alright, so here the charge is minus 3 plus 3, 0, neutral. So this is your cis. Now in case of Trans, what it will be, you can say this is, in case of trans, clear, see that. So here what will I do? That is, anyway I can bring it. So what will I do is that I will bring here, that is Cl, Cl, and that is NH3 here, that is nothing but one more, that is sorry, here that is Cl, I'll bring it here, Cl I'll bring it here, this is NH3, it is already there, this two, and the interchanging is taking place. Alright. So what I have done is, that is, you can see here, that is I have interchanged, that is, so ClNH3, this is same. Alright, and here what it is that this ClNH3, or I can say this ClNH3, I have changed it. Alright, so in this way you got the diagonals to be the same, that is, so it is known as what? It is called as trans. You will say this is a diagonal. Yes, this is a diagonal. In octahedral complex, this is your diagonal, we can say that. So here it can be, that is nothing but, we can say it is, what is that? Ma3b3 ion complex. So this particular one, it's also called as facial. Alright, the cis isomer, it's said to be as the facial, FAC, we can say that. And the trans, it is said to be as meridional, or that is peripheral, we can say that. Isomers, we can say that. Clear? So the isomer, that is, which is known as meridional or peripheral, that is a trans, and the other one, that is said to be as the facial, that is your nothing but known as a cis isomer. This is just a different name we are giving to it. Alright, a different name. And we can have the another one is MAA2, we can say that. We can have another isomers, then we can draw it and we can see it down. So hence these are the different types of geometrical isomers in case of 4 coordination spheres and 6 coordination spheres. One more I have left with you, that is MAA2A2. Where, what I said? MAA2, that is AA2, A2, N plus minus. Here same thing, it is a bidentate ligands, and here that is your monodentate ligands, so to say. So here AB and AA, what is the difference? In the previous case I said AB, alright, and here AA. So here what you find is that I said you AA because the ending and the starting both are same. Ending and starting means, that is NH2, CH2, CH2, NH2. So it starts with NH2 and ends with NH2. So NN. So hence it is AA. We can say that. Are you getting me my point? So hence it is said to be as MAA2, but you will draw it. This one. You will draw it. This one. So what is that? MAA2, A2. We can say that. N plus minus. Clear? Again, A is any monodentate ligands. It can be Cl, Br, I, NH3, anything it can be. Monodentate ligands. And AA means you have to take such a ligand in which the starting and the ending atom should be same. So the best is your ethylene diamine, NH2, CH2, CH2, NH2. Finished. Got it? So there it was different. In case of glycine, it was NH2, CH2, CO. So starting was N, ending was O. So hence I differentiated in this way. See, it is up to you. How do you differentiate it? Alright, so there it is AB because both the atoms was different, the starting and the ending. And here both the atoms are the same. So hence I have kept it as AA. Alright, clear? So this is about your geometrical isomers, so to say.